So, we will continue our discussion on principle of hydraulic machines and system design, and today we will discuss about turbine specific speed and we will work out a few examples. So, we have discussed that specific speed and we have derived the expression of specific speed for pump. Similarly, today we are going to derive the specific speed of the turbine, because this is very important. So, what is specific speed? That is probably we have discussed that it is a speed of a geometrical similar machines. So, in the context of the discussion of pumps, we have discussed that the speed of a geometrical similar machine which produces unit discharge when working under unit head in case of a pump. So, now we will see what is the definition of specific speed for the turbine. So, I am writing that it is defined as the speed of operation of a geometrically similar model of the turbine which is so proportional that it produces unit power when operating under unit head. It produces unit power when operating under unit head or when working under unit head. So, when operating under unit head. So, similar to the definition of specific speed of a pump, it is defined as a speed of a geometrically similar model. I mean geometrically similar, that is we have discussed that it is identical in shape, not in size may differ but shape will remain same, of the turbine which is so proportional that it will produce unit power when working under or operating under unit head. So, now let us try to derive the expression of specific speed. So, what is power? Normally, that is again I am repeating that based on the direction of energy conversion, we have classified one turbo machines into pump and turbines. So, pump mechanical energy is converted to increase the stored energy of the fluid, while in case of a turbine you are utilizing the stored energy of the fluid to obtain the kinetic energy rotation of the runner, rather kinetic energy, and we are obtaining power. So, what is power obtained from the turbine is rho cube G into H, where H is the working head. So, now question is, from here I mean if rho is constant and G not varying, so power is varies as what is Q into H is very important. So, Q is equal to A into velocity into H, where A is the cross sectional area and V is equal to water velocity, right. So, what is A? So, it is therefore write P varies as A is equal to pi by 4 d square. So, d square into V, that is again root 2 G H into H. So, D is the wheel diameter or diameter of the runner, wheel diameter, and H is the net head of water or net head or water available, and U is equal to maybe so this is the expression P is equal to d square root Tgh into H. Now, question is U, which is blade velocity, which is varies as V, because U is equal to let us say blade velocity at the inlet or outlet, whatever it is maybe, but if it is axial flow machines, axial flow turbine U1 is equal to U2. So, U varies as V. So, U is equal to what? U is equal to pi dn by 60, therefore, dn varies as root 2 Gh. Therefore, I can write d varies as root 2 Gh by n, that is root h by n. So, we are obtaining this relationship. So, this is 1, this is 2. So, from 1 and 2, how I can write? So, if I replace the value of d in expression 2, so if I go to the next slide, then that means using 1 and 2, using 1 and 2, what I can obtain? P varies as d square, that is what you obtain, d square root 2h into h. Therefore, d square into root h into h, where d square is equal to how much? Is equal to h by n square into h power 3 by 2, that is h to the power 5 by 2 into n square. So, this is the power that is we obtain. U varies as v because the plate velocity depend upon the of course the velocity of water, I mean that is striking, that depends, so they are proportional based on the, if velocity of water increases, the plate velocity will increase. Now so from there I can write that n varies as h to the power 5 by 4 divided by p to the power half. Now this proportionality I can remove by using a constant, so that is k into h power 5 by 4 p power half, where k is equal to proportionality constant. Now from the definition itself, so what is k? K is equal to n p power half by h power 5 by 4. So what is proportionality? To obtain the magnitude of proportionality constant, we have to define the definition of we have to use the definition of the turbine specific speed. So what is definition of specific speed? So that means P will be 1 unit, when h is equal to 1 unit, right, and then n will be equal to ns. So when working under or operating under unit head, it will develop unit power, then it is specific speed. So therefore I can write that specific speed, rather k equal to ns 1 divided by 1, that is equal to ns. Therefore I can write n is equal to ns h power 5 by 4 to divided by 5 p power half. Therefore specific speed is equal to n p power half divided by h power 5 by 4. So this is the specific speed of the turbine. So this is dimensional specific speed, of turbine, right. So we have derived the expression of dimensional specific speed of the turbine similar to what we have derived in case of a pump, where the definition was little bit different, because that will discharge unit under when working under the, so whenever specific speed of the pump was different, because that was only Q and H. So when working under unit head, it will deliver unit discharge. So but it will now produce unit power when working under unit head. So based on that, we have derived the proportionality constant using the definition of specific speed, and we have obtained the expression of specific speed, that is n p power half by h power 5 by 4. Now so this is dimensional specific speed. Now to obtain the dimensionless specific speed, again we have to divide it by g power g. So because it is not dimensionless, so in a dimensionless, we should know in dimensionless form, it will be the specific speed n will be n root p divided by g h 5 by 4 into rho power half. So rho is the density of the fluid. So this is dimensional form of the dimensionless specific speed. So this is dimensionless specific speed. Now we have to know some scale ratio, because that is very important. We will work out a few example. So what is scale ratio? As I seen that U varies as V. So from here I have obtained dn varies as root of h, because U is equal to pi dn by 60, V is equal to root h, U is equal to pi dn by 60 and V is equal to root 2 gh. So dn varies as root h. So from there I can write root of h1 by d1 n1 is equal to root of h2 by d2 n2. Probably from there h1 by n1 square d1 square is equal to h2 by d2 square n2 square, and this is I have derived using Buckingham pi theorem when we have derived the dimensionless term for the operation of pumps. So that is similar again, because pump and turbine are basically all are hydraulic machines. So this H by H by n square d square is known as flow coefficient. So we have obtained this pi term when we have used the Buckingham pi theorem to obtain a few dimensionless terms. So this is flow coefficient. Similarly, we know q by n d cube, that is equal to what? So this is head coefficient, sorry, H by n square d square is equal to head coefficient. Similarly, q by n d cube is equal to flow coefficient, and p by n cube d power 5 is equal to power coefficient. So these three dimensionless term we have derived, rather we have obtained using Buckingham pi theorem when we have did this analysis in the context of pump operation. So from this I can write that again q1 by n1 d1 cube is equal to q2 by n2 d2 cube. This is very important, rather because the pump of homologous series, rather turbine of homologous series, that is geometrically similar, identical in shape not in size. If we know the head discharge diameter at a particular speed, we can obtain the other things at when it is running at different other speed. Similarly, I can write P1 by n1 cube d1 to the power 5 is equal to P2 by n2 cube d2 to the power 5. So these are different scale ratio affinity laws that we have discussed. So now this is very important. Now question is, we have to also obtain a few things. What is unit power and what is unit speed? So what is unit speed? Unit speed nu, it is the speed, I am writing, it is the speed. So all of these the scale ratio, and this is important to obtain when a turbine or pump is, if I need to obtain the power when turbine or pump is operating at a different speed, when impeller diameter or runner diameter is different. So it is the speed of a geometrically similar turbine working under unit head. So it is the speed of a geometrically similar turbine working under a head of 1 meter. So U varies as V, that is what we have seen. So from there pi dn by 60 varies as root of gh, therefore n varies as root h. So n is equal to k into h. So nu will be equal to k root h, n is equal to n by root h. So this is the unit speed. So if I use the definition, then I can easily find out the proportionality constant, and the unit speed is the n by root h. Similarly, unit power, that is Pu, that is what again we can define, that it is a kilowatt of power generated by a geometrically similar turbine working under a head of 1 meter. So Pu, so it is the kilowatt of power generated by a geometrically similar turbine working under a head of 1 meter. So how I can derive? I know P is equal to rho Q into G into H, that is what I know. So that is rho into area into velocity Q into G into H, right. So therefore rho A into V is equal to root 2 GH into G into H. Therefore I can see that P varies as H power 3 by 2. P varies H power 3 by 2. Therefore P is equal to K, again K1 into H power 3 by 2. So it produces 1 kilowatt when working under unit head. Therefore K is equal to Pu. K is equal to Pu. Therefore P is equal to P unit power to the power h by 3 by 2, therefore unit power that is equal to P by h power 3 by 2. So this is the definition of unit power. So this is the definition of unit power. So we have obtained the definition of unit power and unit speed. Similarly, unit discharge. What is unit discharge? So again this is cube u, suffix u. So it is the flow rate of a geometrically similar turbine under a head of flow rate of a geometrically similar turbine working under a head of 1 meter. So we know Q is equal to A into V is equal to A into root 2 GH. Therefore Q varies as root H. So Q is equal to K2 into H power half. So if I use the definition of unit discharge, then K2 is equal to cube U. Therefore cube U, that is unit discharge, will be equal to Q by H power half. So this is unit discharge. So we have obtained unit discharge, unit power and unit speed. So these three will be important while we are solving a few problems. So now with this, let us move to solve a few problems. So first problem I will be solving, that is very important, that problem is a quarter scale turbine model is tested under a head of 10.8 meter. The full scale turbine is required to work under a head of 30 meter. The full scale turbine is required to work under a head of 30 meter and to run at 7.14 revolution per second. 7.14 revolution per second. At what speed the model be run? At what speed the model, at what speed must the model be run? Model be run. If it develops 100 kilowatt, if it develops 100 kilowatt and uses 1.085 meter cube of water at this speed, then what power will be obtained from the full scale turbine? Power will be obtained from full scale turbine. So and what will be the dimensionless specific speed of the full scale turbine? What will be the dimensionless specific speed of the turbine? So we have to solve this problem. How we can solve? So what is given? D by dm, model and full, is equal to 4 by 1, hm is equal to 10.8 meter, h is equal to 30 meter, n is equal to 7.14 revolution per second, that is given. So we have to find out Nm is equal to how much, Pm is equal to 100 kilowatt, Qm is equal to 1.085 meter cube per second, then P is equal to how much. So this is the problem, very easy, because you can use the scale, singularity variable, that is scale ratio. So how can you use ZH by n square d square is equal to GHM by model in nm square into dm square. From there nm square is equal to d by dm square hm by h into n square. We know every quantities, and if we put, we will obtain nm is equal to 17.136 revolution per second, because I know d by dm, I know hm by h, and I know n, so I can obtain nm will be this. So this is the at what speed the model must run. So 17.136 revolution per second. Similarly, if I go to for the next task, that is, so if I use p by rho n cube d to the power 5 is equal to pm by so if I go to my previous slide, here it will be rho 1 rho 2. So if I now write, so rho m nm cube dm to the power 5, right. So p will be equal to, you know, nm, rho and rho m will be same because liquid is not changing, liquid is not changing, so rho m and rho will be same. So nm by n by nm whole cube d by dm tar whole to the power 5 into pm. I know every quantities, I know nm already, n I have calculated, nm I have calculated, d I know, dm no, pm I have no. So pm is equal to 100 kilowatt, so this is 100 kilowatt. So the actual will be 7.40 megawatt. So that is what we obtain. And dimensionless specific speed, that is dimensionless specific speed will be equal to n root p by rho divided by g h power 5 by 4. So everything I know, and ultimately I will obtain, that is 7.14 into root of 7.40 divided by into 10 power 6 divided by 10 cube divided by 9.81 into 30 to the power 5 by 4, and ultimately I will obtain 0.503. So this is the dimensionless specific speed. Okay, so this is one problem. We can solve another problem very quickly. Problem 2, you know, a Kaplan turbine working under a head of 10 meter, working under a head of 10 meter, produces 3 megawatt power, right. The turbine runs at 62.5 rpm, and it discharges each 350 meter cube per second, and discharge is 350 meter cube per second, 350 meter cube per second. And its discharge is 350 meter cube per second. The tip diameter of the runner is 7.5. Tip diameter of runner is 7.5 meter, and half to tip ratio is equal to 0.43. For this turbine, evaluate the following. For this turbine, evaluate the following quantities. Number 1, speed ratio, flow ratio, unit power, unit discharge. Speed ratio, B flow ratio, C unit power, unit discharge. Unit power, D unit discharge. How I can calculate? So runner tip speed, so solution. Tip ratio diameter is given, half to tip ratio 0.43 is given. So runner tip speed U is equal to pi diameter of the tip by n by 60. N is equal to given, n is equal to given 7.5, 62.5 rpm. So it will be coming around pi into 7.5 into 62.5 divided by 60, 25.5312 meter per second. Given dH by dt is equal to 0.43. Therefore, dH will be equal to 0.43 into 7.5, that equal to 3.225 meter. So, flow velocity I can obtain, flow velocity let us say let us say CA is equal to Q divided by pi by 4 into tip diameter square minus half diameter square dH square, and ultimately I will obtain 350 into 4 divided by 7.5 square minus 3.225 square, and that will be equal to 9.72 meter per second. So, what is now, if I go, then I will obtain speed ratio. Speed ratio, that is u by 2gh. Speed ratio is u by 2gh, u by v, that is obtained, that equal to obtain 24.5312 divided by root 2 into 9.81 into 10. So, I will obtain 1.75. Flow ratio, that equal to how much? Flow velocity CA divided by root 2 gh, that equal to 9.72 by root 2 into 9.81 into 10, that I will obtain 0.6939. Unit power, that we have already now defined. What is unit power? P by h power 3 by 2, h power 3 by 2. What is P? 3 into 10 power 6 divided by h is equal to 10 power 3 by 2, and that will obtain 9.4 into 10 power 4. And unit discharge, that equal to Q divided by root over h. What is Q? 350 divided by root of 10, and ultimately I will obtain 110.679. So, we have solved that these two problem, and based on, because how, so in summary I can tell that we have we have derived the specific speed of the turbine. From there we have defined scale ratio, then from there we have defined a few ratio like some power, unit discharge and unit head, and we have worked out two example how to solve the problems. Probably it will help you to work out a few examples and it will help you to get an insight about that how to solve a problem and how to calculate different ratios based on the data available. So, with this I stop here today, and I will continue the next class about the some important points related to cavitation of a turbine and how we can prevent cavitation and the mathematical expression for the cavitation. Thank you very much.